Welcome to The Explainer. Today, we're diving into what was, for a long time, an impossible task in manufacturing. Trying to weld steel to aluminum. You've got strong, high-temperature steel on one side and lightweight, low-melting point aluminum on the other. Trying to fuse them with a blast of heat? Well, that's just a recipe for a complete mess. So, how did engineers finally crack this code? They invented a process that isn't about brute force, but about a beautifully precise, high-speed dance.
First, we're going to dig into why that weld was considered impossible in the first place. Then, we'll get to the cold revolution that changed everything. We'll pull back the curtain on the secret, this incredible dancing wire, and see how it can be digitally tuned for a perfect result. And finally, we'll look at the mind-blowing future it's building, literally, with 3D printed metal.
Okay, so you're trying to build lighter, more efficient cars, lighter planes. Joining strong steel to lightweight aluminum seems like a no-brainer. It's the holy grail. But if you talk to any welder, they'll tell you that using a traditional torch to do this, it's a total nightmare. When you try to fuse them with raw heat, you run into two huge, absolute deal-breaking problems.
So, the first problem is just basic physics. They are completely incompatible partners. Steel, you see, needs a ton of heat to melt, but aluminum has a much, much lower melting point, and on top of that, it acts like a heat sink, just sucking that energy away like crazy. So by the time you finally pumped enough heat in to get the steel to melt, that heat has already warped and destroyed the aluminum right next to it. It's kind of like trying to toast a marshmallow in a rock with the same blowtorch. It just never ends well.
But you know what? Even if you could somehow manage the heat, you'd slam into an even bigger problem. At the microscopic level where the molten aluminum and steel touch, they have a chemical reaction. They form something called an intermetallic compound. And you can think of this stuff as basically a microscopic layer of glass that forms right between the two metals. As researchers have pointed out, this incredibly brittle layer is the real killer. It's the fundamental reason why these joints are just doomed to crack and fail under any real stress.
So, if heat is the enemy, how in the world do you solve this impossible weld? Well, you don't just turn down the thermostat. You have to change the rules of the game completely. You invent a process so different, so low energy, that it actually earns the name cold metal transfer, or CMT. And this isn't just a slightly cooler arc. We're talking about a complete reinvention of how you use energy to create a bond. And these numbers right here tell the whole story. To do the exact same job, the CMT process puts over 75% less heat into the metal compared to conventional welding. That is the breakthrough. This huge reduction in energy is what starves that brittle, glass-like layer we talked about. It keeps it from growing thick enough to cause the weld to fail. It's how you finally join steel and aluminum without destroying them in the process. Okay, so how does CMT pull off this low-heat magic trick? It's not actually cold, of course. The real secret is in a stunningly fast and precise mechanical action. It's a high-frequency dance performed by the welding wire itself.
Right. So instead of a constant brute force electrical arc blasting away, CMT works in this rapid four-step rhythm. And this cycle repeats up to 70 times every single second. The absolute genius is in step 3. The machine doesn't just push the molten metal across a gap. It physically pulls the wire backward, using mechanical force to just neatly dip a droplet into the weld.
Let's actually break down that high-speed dance frame by frame. So it all starts pretty normally. A low-power arc creates a little molten droplet at the tip of the wire, and that wire starts moving forward. But the very instant it touches the workpiece, the system detects a short circuit. And then it does something brilliant. It cuts the welding power to almost nothing. This is so important. It means there's no violent electrical explosion, no spatter flying everywhere at that critical moment of transfer.
And here it is. This is the secret sauce. With the power cut, a motor inside the torch physically yanks the wire backward. This little mechanical tug is what pinches off the droplet, using its own surface tension to just gently dip it into the pool with almost no extra energy. Then the arc reignites, and this whole elegant cycle starts all over again, 70 times a second,
Just incredible. Now, this dancing wire thing is more than just a really clever mechanism. Because the whole process is digitally controlled, it becomes this tunable instrument. It gives welders an amazing set of dials, letting them craft the absolute perfect weld for any job.
So, two of the most important dials here are dynamic correction and arc length correction. The easiest way to think about it is like this. Dynamic correction, or DC, adjusts the current. That's like controlling the physical push that the droplet gets. Then arc length correction, ALC, adjusts the voltage and the timing. That's like controlling the heat and the duration of the arc itself. And this level of fine-tuning has some really profound results, just as researchers have noted. Using these digital dials, a welder can control exactly how much the base metal melts and mixes in. That property is called dilution, all without changing the basic speed and power settings. I mean, that is a level of surgical precision that traditional welding just can't touch. Look at this control in action. This data shows a direct cause and effect. You crank up the digital setting for arc length correction, and what happens? The actual time the arc is on gets longer. The result is a deeper wire weld, all without changing how fast you're feeding the wire. You're literally reshaping the properties of the weld bead with software. That's a total game changer, especially for delicate jobs. This amazing control over heat and material doesn't just help us solve old problems, though. It actually unlocks an entirely new frontier, building huge things at high speed with metal 3D printing. The technology is called wire arc additive manufacturing, or WAM for short. And what's happening here is instead of joining two parts together, a robot arm uses the CMT process to literally draw an object in 3 dimensions, building it up layer by layer from a spool of welding wire. And CMT's low controlled heat is the perfect engine for this, because it stops the object from warping and twisting as it gets bigger. And because this whole thing is built on a welding platform, WAM is unbelievably fast. A lot of those fancy powder-based metal 3D printers, they deposit material in grams per hour. WAM, powered by CMT, can lay down up to 4 kilograms in that same hour. That's not just a small improvement, that's a massive leap in scale. It suddenly makes it possible to print enormous parts, like whole aerospace components or really complex structures for building.
So what's the big picture here? What does this all add up to? Well, it's the power to build huge, complicated metal parts on demand, with almost zero waste. It's the ability to create totally unique bimetallic objects, maybe starting with steel and then switching to a nickel superalloy, all in a single print. And it's a way to precisely repair a super expensive part, like a turbine blade, saving something worth thousands of dollars from being thrown on the scrap heap. So in the end, a process that was born just to solve one impossible weld has now given us a completely new way to build our world. The journey from that simple, frustrating problem to this new frontier really leaves us with one big question. What new possibilities open up when we can 3D print massive, high-strength metal structures on demand anywhere we need them?